Hey everybody, welcome back. And with this presentation, I'm going to talk a little bit about density and temperature and some properties that I hadn't covered before. So the first thing I'll talk about is density, and that is covered in section 1.8 in your book. And the next thing I'm going to do is sort of digress and talk about the differences between extensive and intensive properties, which is covered in 1.2 of your book. And then finally, I'm going to go over temperature scales, which is covered in 1.9 of your book. Okay, so first let me talk a little bit about density. So what density is, it's a quantitative measure of how much mass you have in a particular amount of space for any kind of matter. So when you think about density, you can think about, well, what is going to affect the value of density? So one thing that's going to affect the value of density is consider that you have two pieces of matter about the same volume. How can you increase the density? One way you can increase the density is by packing more atoms into that space. And so some matter can be more dense is because there are more atoms of that matter packed in that space. But another reason why something can be more dense is because each of those atoms maybe weighs a lot more than, say, another sample that is less dense. And so that is a good an example of that is, for example, comparing the density of gold to aluminum. Gold has a density about 7 times of that of aluminum. The main reason why gold is more dense than aluminum is because even if you had equal volumes of gold and aluminum, gold atoms individually weigh about 7 times more than the aluminum atoms. And so you have a lot more weight for an equivalent amount of volume. So the way you measure density is you take the mass of an object and divide by its volume. And so the formula there is D equals M divided by V. And so the SI units for density are kilograms per meters cubed. And so we don't really use those units very often in density problems. Another thing to note is that that unit is not really a base unit. It is a derived unit. So it's derived by taking a mass unit, which will be a base unit like, say, grams, and then dividing that by a derived unit, which would be volume. That, for example, would be meters cubed. So most of the time, we measure density in 2 other units. One unit is grams per cm cubed, but the value for grams over cm cubed, because 1 milliliter is equal to 1 cm cubed, that value will be equivalent to grams per mil. So grams per cm cubed or grams per mil should be equivalent. Those are the 2 values we use most of the time in density. But keep in mind, if you see a problem and you see some units and you see some kind of mass unit divided by a volume unit, that is considered a unit of density, although it may not be the usual units you would recognize. So for example, you might see in a problem grams per meters cubed, that is mass divided by volume, or micrograms per mil. Again, mass divided by volume, so those are density units. Okay, so we're going to do a few simple density problems. And so the first one, problem A, is what is the mass in grams of 417 milliliters of ethylene glycol if the density of ethylene glycol is 1.11 grams per mil? So to solve this problem, I think maybe the best approach is just to write out the formula, then write out the variables and assign them. So let's go ahead and write out the formula, which is D is equal to mass over volume, D being density, and then we have mass, and then we have volume. So density, D is 1.11 gram per mil. M is what you're trying to find out. V is 417 mils. Okay, so the first thing we want to do is we want to take D equals mv and then rearrange the equation so we have m by itself. And so here's how I might approach that. So what I'm going to do is I'm going to take this equation and multiply both sides by v like this. And so here on the right side of the equation, the v in the denominator now cancels out with the v in the numerator, and so the v's are gone. And so I'm going to rewrite the equation. We have m is equal to d times v. So it looks like we have now solved the equation for m, which suggests that if we just kind of plug in numbers, we'll go ahead and get the answer. So let me go ahead and do that. So M is equal to D, which is 1.11 grams per milliliter, times V, which is 417 milliliters. So if you do the math on the calculator for that, you should get the answer, which is 463 grams. Okay, so we'll do problem B. What is the volume of 242 grams of ethylene glycol in centimeters cubed? Okay, so again, this is going to be density equals mass divided by volume, and so we'll assign variables D, M, and V. And so density again is 1.11 grams per milliliter. Mass, we know this time, is 242 grams, and volume is what we're trying to find. So again, what we want to try to do at this point is solve this equation for V. So we got to get V by itself. So the first thing I'm going to do is, you can see I have V here on the right side of the equation in the denominator. So what I want to do is multiply both sides by V, and that way V will go to the left side of the equation, it'll be in the numerator. So I'm going to multiply by V here. And then you can see here V cancels out. And so we're at kind of where we were at before, where we have M is equal to V times D. Now, what we want to do is we want to solve for V. So we want to get rid of D from this side of the equation. So we can divide both sides of the equation by D. And so if we do that, we get M over D is equal to V. And so now we have solved for V, so we should be able to plug in those numbers into M and D and find out what V is. So M is 242 grams, and D is 1.11 grams per mil. And let's see what the units should be in the answer. So one thing you can see is you have grams in the numerator will cancel out with grams in the denominator here. How about mils? We have mils in the denominator of a fraction, which is in the denominator of another fraction. If that's the case, then it goes up into the numerator. So the answer should be in milliliters. And so if you take 242 and divide it by 1.11, you should get 218 milliliters. Now, the problem wants the answer, it looks like, in centimeters cubed. And so what we learned recently is that for every 1 milliliter you have also 1 centimeters cubed. So if the answer is 218 milliliters, it's also 218 centimeters cubed. Okay, we'll move on. Okay, so now what I want to do is talk a little bit more about properties. And so I want to talk about the difference between extensive properties and intensive properties. And so what an extensive property is, it's some kind of property whose value does depend on the amount of matter you have. While an intensive property is some kind of property whose value does not depend on the amount of matter you have. It is independent of the amount of matter you have. So let's go over some examples first of extensive properties. So a great extensive property is mass. So imagine again we have a brick, and let's say that you have enough matter in the brick so that its mass is 1 kilogram. And now let's say you broke the brick in half, and so you're looking at one of those pieces, and you can see that that piece has half the matter that it had originally. So the question is, we've reduced the amount of matter in that piece. Does it have the same value of mass? And the answer is no, it's going to have half the value of mass. Now it'll be something like 0.5 kilograms. So what you can see is that the value of mass is going to depend on how much matter you have. And this is also true for volume. If your brick had 1 liter of volume and you broke it in half, it's going to have less matter in that piece, and so it'll have less volume as well. And so the volume is going to depend on how much matter you have. Another extensive property is length. You can imagine that the length of something is going to depend on how much matter that you have. Now let's compare that to some intensive properties. And so a really nice example of an intensive property is the boiling point of a liquid. So imagine that you say had a thimbleful of water, and let's say you boiled this thimbleful of water and you measured the boiling point of that thimbleful of water and found it was to be 100.0 degrees Celsius, sort of as expected. Now, let's say you had a tub full of water. You had a lot more water. You had a lot more matter, a lot more water, and you boiled that tub full of water. The question is this: would it have a different value for the boiling point? It would have the same value of the boiling point. It would have exactly the same value of the boiling point. So what you can see is boiling point is a property whose value does not depend on the amount of matter you have. Another example would be melting point. Another example would be viscosity. So what's viscosity? Viscosity measures how fast a liquid runs out. So whether you're looking at a little bit of motor oil or a lot of motor oil, they're going to have exactly the same value of viscosity because it's an intensive property. The value will not depend on how much matter you have. And another important intensive property is density. So how can you figure out if a property is either intensive or extensive? What you can do is sort of do a mental test. Think of the property and ask yourself this question: does adding more matter to the property affect the value of that property? If it does, it is an extensive property. On the other hand, in your imaginary test, you add more matter, it does not seem to affect the value of the property, then that would be an intensive property. Okay, so now what I want to do is talk a little bit more about why density is a useful intensive property. The reason is a lot of times density will allow you to identify the kind of matter that you have. So let's say you have a chunk of matter and you don't know what the matter is. It's some kind of substance and you're trying to figure out the identity of that matter. So let's take a look at some properties and see if these properties would be useful identifying that kind of matter. So the first property we may look at will be mass. And so you can look at the mass of this matter. So the question is, would mass allow you to unequivocally identify the kind of matter that it is? And the answer is no. And the reason is, if you say were to measure the mass of this matter and it found to be 0.5 kilograms, well, you know that all other kinds of matter that exist can also have that value. So the value of that matter, of the mass, does not really help you in identifying it. Would the value of the volume of the matter help you in identifying the matter? And the answer is no. So you can measure the volume, let's say it's 1 liter, but again, you know that all different kinds of matter can have that same value of volume. So how about density? Density is a little different. You take that mass value and divide it by the volume, and that will give you density. So would the value of density allow you to identify the matter? And the answer is yes. And the reason is that, one, it doesn't matter how much matter you have. It will have the same value of density. So it's going to be independent of the amount of matter that you have. The value of the density will be unique to a particular kind of matter. And so what you can sort of see there is I have sort of a list of substances, and all these substances have different values of density. And so density can be used to identify different kinds of matter. The next thing I want to do is talk about temperature scales, and there are 3 of them that you need to know. They are the Celsius scale, the Kelvin scale, and the Fahrenheit scale. So let me first talk about the Celsius scale because it's probably the easiest to remember. So the Celsius scale was developed by a man named Celsius, and what he did is he took water that was freezing and stuck a thermometer in it, and he set that temperature to be 0 degrees Celsius. Then he took some water that was boiling and stuck the same thermometer in it and marked that to be 100 degrees Celsius. And then he put 100 degrees between 0 and 100, between the freezing point of water and the boiling point of water. So it's a pretty simple scale. Now, the Kelvin scale is actually pretty simple also, because all you have to do is, if you have a Celsius temperature, all you have to do is add 273.15 degrees to it to get a Kelvin temperature. So the freezing point in Celsius is 0. Therefore, the freezing point of water in Kelvin is 273.15 degrees. The boiling point of water in Celsius is 100 degrees. So the boiling point of water in Kelvin is just 273.15 added to that. It should be 373.15 degrees Kelvin. So what you can see is on the Kelvin scale, between the freezing point of water and the boiling point of water, there are 100 degrees between them. It's just that the numbers are offset. So it might bring up the question as to what is going on at 0 degrees Kelvin. Well, if you have a substance that is that cold, what is going on there? It is so cold that there's really very, 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 very little energy in the individual molecules in that substance. So absolute zero is the theoretical place where you would have molecules that have absolutely no energy. And as you may know, we have never, I don't think, ever gotten down to absolute zero. Okay, so let me talk a little bit about the Fahrenheit scale. The Fahrenheit scale is a little bit different with the numbers, and so you may know something about it already. So you can see that the freezing point of water in the Fahrenheit scale is not 0, but 32 degrees Fahrenheit. The boiling point of water is not 100, it is 212 degrees Fahrenheit, so you probably want to memorize those numbers. Another thing you may notice is that with the Celsius scale, there are 100 degrees between the freezing point of water and the boiling point of water. In the Fahrenheit scale, there are not 100 degrees, but 180 degrees, which basically means that the width of a degree in the Fahrenheit scale is a lot less than in the Celsius scale. So we have here a formula that you can use to convert a temperature in Celsius into Fahrenheit. It is a Celsius times 1.8 plus 32 should give you the temperature in Fahrenheit. One final thing, so you might wonder why Fahrenheit decided to set the freezing point of water to be 32 degrees Fahrenheit and the boiling point of water to be 212 degrees Fahrenheit. That seems kind of arbitrary. And the reason is, what he wanted to do was find a solution that was as cold as he could possibly get it and set it to 0 degrees Fahrenheit. And so what he found was if he mixed equal portions of ice and ammonium chloride, the ammonium chloride is an endothermic salt and it'll cool down the ice below 32 degrees Fahrenheit. And so he set that temperature to be 0 degrees Fahrenheit. Then what he did is he said, well, I want body warmth to be 100 degrees Fahrenheit. Now we know today that is not exactly true. Body warmth is 98.6 degrees Fahrenheit, so it's theorized that maybe Mr. Fahrenheit had a little bit of a fever when he set that temperature to be 100 degrees Fahrenheit. So based on that scale, the boiling point of water is forced to be 212 degrees Fahrenheit. Moving on, 172.9 degrees Fahrenheit, and we're going to get this into Celsius. And so the formula we're going to use is degrees Fahrenheit is equal to 1.8 times degrees Celsius plus 32. So what we want to do is we want to plug in 172.9 into Fahrenheit and solve for Celsius. So it's 172.9 is equal to 1.8 times degrees Celsius plus 32. So what we have to do is sort of isolate degrees Celsius, and so we have to get the numbers over to the other side of the equation. So the first thing we want to do is get rid of this plus 32. So I'm going to subtract 32 here from the right side of the equation. If I do that, I have to subtract 32 from the left side of the equation. So it's 172.9 minus 32. And so I get 140.9 is equal to 1.8 times C. Okay, and so you want to solve for Celsius, and so what you want to do here is you want to get rid of the 1.8. So you want to divide both sides of the equation by 1.8. So degrees Celsius is going to be 140.9 divided by 1.8. And I get 78.3 degrees Celsius. Okay, thank you for listening to that, and we will talk to you later.